This screencast continues our journey through the one-way analysis of variance hypothesis test. We're working through step 4 and developing the definition of the test statistic, MSA over MSW. In the previous screencast, we developed two measures of variation, SSA, measuring the variation between sample means, and SSW, measuring the variation within samples. We remarked that SSA, relatively large compared to SSW, indicated definite spread between sample means, which in turn is evidence that the population means differ. That is, evidence in favor of H1. Recall, the letter C generally indicates the number of populations involved in the hypothesis test. In our problem, C is the number of stores, that is, C is 2. The letter N represents the total number of observations in all samples. In our problem, N equals the total number of cash register receipts from both stores, that is, N is 10. We now develop the actual test statistic. We need mean square measures of sample variation. The first is the mean square amongst sample means, MSA. It's simply the sum of square amongst sample mean variation divided by the number of degrees of freedom associated with SSA, and that is C minus 1. In our case, we found SSA to be 1,000, and C, of course, is 2 stores, so 2 minus 1 is 1. We have MSA is really the same as SSA, 1,000. What MSA measures is the average amount of separation between the sample means, where the average is taken over the number of samples minus 1. Our next mean square measure is MSW. MSW is defined as SSW divided by N minus C. We had previously computed in our example SSW equal to 728, N being the total number of cash register receipts in both samples minus the total number of samples, 2. 10 minus 2 would be 8. 8 divided into 728 is 91. MSW is a measure of the mean or average amount of separation between the observations within each of the samples and their respective sample means. Again, and more accurately, MSA, relatively large compared to MSW, is evidence in favor of H1. We are now in a position to define the test statistic. It is simply MSA over MSW. And as we've discussed, large values of MSA over MSW favor H1. That is, favor that the population means actually differ. Now that we've developed an intuitive understanding of what the test statistic does, we next need to identify the test statistic's probability distribution. The value of the test statistic, along with its probability distribution, will allow us to determine whether we can conclude that the population means actually differ without taking more than a 5% chance of being wrong. 5% is the significance level of the test. The result on the next page will tell us about the probability distribution of the test statistic. The result says, when the model assumptions hold, that is, when the samples are random samples that were obtained independently of each other, when the populations are normally distributed, and when the population variances are equal, then our test statistic, MSA over MSW, is distributed as an F distribution with C minus 1 degrees of freedom for the numerator and N minus C degrees of freedom for the denominator. Generally speaking, results such as this one require proofs. In statistics for managers, we won't prove anything. We'll simply state such results. It will be your responsibility to have an understanding of what those results say. In our particular example of the two stores, C minus 1 is 2 minus 1 or 1, and the total number of cash register receipts in the two samples is 10. 10 minus 2 is 8. This is indicated here. We'll talk more about an F distribution in several pages. It is important for us to understand the entries on an ANOVA table. It's simply a table that allows us to keep track of all the quantities we've computed along the way. In the extreme left column, we put down our sources of variation. Among group variation, for example, our sum of square measure of that is SSA. Within group variation, for example, our sum of square measure of that is SSW. And our total measure of variation, or if you wish, overall measure of variation, which we'll call SST. We haven't yet talked about SST, so for now we'll consider it as simply the sum of SSA and SSW. So to complete this table, you would put in what we've computed for SSA, what we've computed for SSW. You would sum SSA and SSW to get SST. You would then put in C minus 1, the number of samples minus 1. You'd put in N minus C, the total number of observations in all the samples minus the number of samples. And then you could do one of two things. You could either sum these two, or you can just put in N minus 1 because you'll get the same thing. And then you put in the MS quantities, the mean square quantities. You get the mean square quantities simply by taking what's in this cell, SSA, and dividing it by what's in this cell, C minus 1. That's MSA. To get MSW, you'd simply take what number you put in this cell, SSW, divided by its degrees of freedom, N minus C, and you'd get MSW. Having obtained MSA and MSW, you simply divide MSA by MSW, and you get the value of the F statistic. And finally, you'll have to compute the p-value, which we'll talk about also in several pages when we talk about the F distribution. Here is a U-try problem. I've recorded here some of the values we've observed so far in our two-store problem. C equals 2 stores. Total number of cash register receipts is 10. We computed the value of SSA, the measure of amongst sample mean variation, at 1,000. The measure of within sample variation, SSW, we computed to be 728. The U-try problem is simply put all of this information onto this ANOVA table, complete all the values up to the p-value, which is introduced below. Since large values of MSA over MSW favor H1, the p-value can be computed as the probability of observing evidence more favorable to H1 than the obtained value of MSA over MSW, which would be up here. Said another way, the p-value is the probability of a F18 random variable exceeding 10.98901, which is the value of the F statistic that you've written up here. If you make the computation of what that probability is, and we'll talk about the details of making that computation on the next page, the probability you obtain is around 1%, 0.010619. Now, before you complete the ANOVA table, which by the way you can check your answers for by pulling down the text box on the actual Word document, we might as well complete step 5. Step 5 is actually expressing your decision. Since the p-value for the hypothesis test, which will be on the ANOVA table up here when we learn how to do that, since that p-value is 0.010619, that is less than or equal to the significance level of the test, 5%, we reject the null hypothesis in favor of H1. In practical terms, this says, at the 5% significance level, the evidence is sufficient to conclude that the population mean cash register receipts actually differ between the two stores. So we've completed the 5-step hypothesis test for the one way of analysis problem. And we've decided at the 5% significance level that the population mean cash register receipts in the two stores actually differ. The final decision was based on the p-value being less than 5%. The p-value was 0.010619, which is, by the way, just a little bit bigger than 1%. So this remark: statistical decisions are not absolutes. If the significance level in the cash register receipt example was 1% instead of 5%, we would have failed to reject H0 since the p-value would be bigger than 1%. That is, if we would have concluded that the population mean cash register receipts were different at the two stores, we would have been taking more than a 1% chance of being wrong. Okay, if you haven't already done it, why don't you go ahead and complete the analysis of variance table. And then I think we'll just make another screencast and talk about the stuff on the next page, the F probability distribution. So go ahead and finish the ANOVA table.